Swayam Prabha. Digital India. Educated India.
Welcome students, this is going to be the last lecture for the basics of fluid mechanics 2, where we are going to see the conservation of momentum in more detail. So starting with the last slide where we left in the last lecture, we derived the general form of Reynolds transport theorem here. So this is the general form. And now in the upcoming lecture and slides, what we are going to do is we will apply this Reynolds transport theorem for derivation of different conservation equations. Okay. So now we are moving from a system to a control volume. So we will see how when we apply B system to mass, what's going to happen. We will see about linear momentum. We will it can also be actually applied to moment of momentum. We are not going to cover that. This principle can also be applied to the energy conservation, which we are also not going to see in this lecture. So we will concentrate morely on mass and linear momentum because this is of maximum use in the upcoming regular lectures and hydraulic engineering course. So yeah, I mean the idea is that we put it all together, this basics of fluid mechanics 2, and proceed to our regular lectures on hydraulic engineering. Okay. So now conservation of mass. How can we apply what we have learned in Reynolds transport theorem to the conservation of mass? So capital B is total amount of mass in the system. When we do the conservation of mass, B, which we saw in Reynolds transport theorem, is the total amount of mass in the system, and small b will be mass per unit mass, which is equal to 1. So we have determined capital B and small b for the conservation of mass. So B is m and capital B is m and small b is 1. So this is the general form of Reynolds transport equation that we have derived in the previous lecture, and also we saw this in the first slide of today's lecture. So this is the control volume equation for the general Reynolds transport theorem, and what we have done here is we have equated B system to mass of the system. As small b is 1, this B is simply this term becomes rho dV, and this also B here is 1, so it becomes rho V dot N dA. So what is this? We know that in the conservation of mass, the total mass of the system with respect to the time dm, capital Dm system by dt is equal to 0. Okay, so we can simply write in the control volume rho V dot Na over the entire cross section should be equal to minus del T times integral of rho dV. This is the equation that we get by substituting B system as mass and capital B as mass system and small b as 1, as we have seen. So this is actually nothing but a continuity equation. So I will just erase all the ink. So it says mass leaving minus mass entering. You remember we saw the property influx was the property leaving minus property entering. Here in this case is mass is equal to rate of increase of mass in the control volume. This equation here tells us that mass leaving minus mass entering is minus rate of increase of mass in the control volume. So now we are going to see So unit vector n here is normal to the surface. So this is the surface 1, which this is normal, and on the surface 2 it is in this direction. So as already indicated by the red arrow, so I will rub this one off, and is pointed out of the control volume in both the cross sections, whether it is 1 or 2, the unit vector is normal to the surface and pointed out of the control volume. So if the mass in the control volume is constant, what we can say, rho v dot n dA is equal to minus del t of rho dV, okay, from the last slide. So there is no rate of change of mass if we assume the mass in the control volume is constant, then this gives rho v dot n dA is equal to, so here we assumed uniform rho on the control surface in this one. So rho can be taken out. So we can simply write for this particular case plus minus rho v bar A is equal to rate of change of mass or m mass per unit time. So we can simply write the velocity, average velocity, as here this quantity integral v dot n dA divided by the whole area of cross section. Okay. So v bar is the spatially averaged velocity normal to the cross section. This is important to note. So now continuity equation for constant density and uniform velocity. So if there are two cross sections, as we have seen in this problem, we can simply write rho 1 v1 dot n1 dA is plus rho 2 v2 dot n2 dA is equal to 0. So density is constant across this entire cross section, right? So this we can take out as indicated by these arrows here, okay. So this one can be simply written as, because the vector here was pointing outward. So if we take this direction as positive, this n1 will be negative, I mean n the vector, that will be negative sign as shown here, minus rho 1 v1 a1 plus rho 2 v2 a2 is equal to 0, because the density is same at the cross section 1 and cross section 2. So rho 1 rho 2 we can take out because it is the same. So this gives us v1 a1 is equal to v2 a2 is equal to q. So using our Reynolds transport theorem, or RTT abbreviated, we obtained equation of continuity. This is same as we saw in fluid kinematics. Okay. So I am going to erase all the ink, and this has a dimension of liter cube per length cube by time, not liter cube, length cube by time. So v1 a1 is equal to v2 a2 is equal to q. This is the simple version of the continuity equation for conditions of constant density. It is understood that the velocities are either uniform or spatially averaged. In both cases, this is the equation of continuity. Okay. So some examples of conservation of mass. The flow out of reservoir, for example, is 2 liters per second. The reservoir surface is 5 meters into 5 meter. The question is, how fast is the reservoir surface dropping? So you see the control surface that we have drawn here, okay. This is the entire height h as already indicated. So the the equation of continuity says from Reynolds transport theorem, rho v dot n dA is equal to minus del t of rho dV, because the total mass of the system, the control volume, is not changing. That is why we arrived at this equation. Okay. So, rho, because it has the same density, so we can cancel these out, right. Take down the ink. So, we get v dot n dA is equal to minus del v del t. Okay. That is the entire volume. If we integrate the volume, the entire volume. So, or we can say q out minus q in, that is the flux leaving minus the flux coming in, is equal to minus dv dt, right. There is nothing that is entering, so q in is 0. So, q out will be simply minus area of reservoir into dH by dt. Okay. Or we can simply write the rate of fall of height with respect to time is this minus q by area of the reservoir. So, dH by dt is the velocity of the reservoir surface. So, this is what we obtain. We can substitute q is given 2 liters per second, we can convert it into SI unit, and area of the reservoir we can calculate because it is rectangular in shape. So, this is also known. So, we are able to calculate dH by dt. I think I will leave this up to you to do the numerical, to arrive the numerical values, which is most simplest that you are able to find. Great. So, now the linear momentum equation. So, an example here is, if you see this figure here, this is, so suppose if you shoot water jet onto a wall, for example, this is one of these example where linear momentum is associated. There is a velocity with which water is approaching, and when it touches this wall, it comes to rest. So, here we can actually apply the momentum conservation, linear momentum. So, what happens is, as I said, we are going to use the same concept of Reynolds transport theorem for the linear momentum equation too. Okay. Here, I mean, in this particular case, the net force is not going to be 0, because this momentum, before hitting there is certain momentum, and after hitting it turns to 0. So, the rate of change of momentum is force, and the rate of change of momentum is not 0. Therefore, force will not be going, I mean, there will be some finite force. So, coming back to our Reynolds transport equation, here what we do is, so this is the control volume equation, as I told you, from Reynolds transport theorem. So, what we do, as we say, capital B in our case, when we want to derive the linear momentum equation, capital B should be mass into velocity, okay, or called momentum. This is very normal term. I mean, in fluid or any type of mechanics, mass into velocity is momentum. I will just take this away, and small b by definition will be the property divided by mass. So, it will be mv as shown here, mv by m. This can get cancelled. So, it is momentum per unit mass. Okay. So, be careful that these are actually vectors. So, now coming back to substituting this capital B here and small b here, and sorry. So, substituting this here and small b here and b here, this is the equation that we obtain. So, this equation, it is going to be dmv dt is equal to rho v dv dot n dA in for steady state, because then if it is steady state, this term will go to 0 for steady state, because there is no change in property with respect to time. So, del t of anything is going to be 0 for steady state solution. So, this is the MA side of F is equal to MA equation. This is the mass into acceleration side of F is equal to MA equation. So, now we, similar to the mass, we assume cross sections here, and we use for the steady state equation the equation that we have obtained in this slide on the next page. So, dm capital V by dt is equal to integral of rho v dot n dA, or in a simpler word, V1, if we are taking this as 1 and this as 2, V1 rho 1 V1 dot N1 dA and V2 rho 2 V2 dot N2 dA. Okay? Or we can simply write it rho 1 V1 A1 into, so this V1 will take care of the direction, and here this V2 is going to take care of this direction because this is pointing outward. If this, we take this direction as positive, so that is why this is negative. Okay. So, assumption is we have taken uniform density, we have taken uniform velocity for writing down this equation. We have taken V is always perpendicular to the area, and we have taken steady state. So, V is the fluid velocity relative to the control volume. So, M1 can be written as minus rho 1 V1 A1 into V1 or minus rho q V1. This is one term, capital M1. So, it is written as minus of rho q into V1, and similarly M2 here can be written as rho 2 V2 A2 into V2 or rho q V2. So, this term here and this term here. So, these M1, M2, V1, V2, V2, this V1 all are vectors. Okay. So, now steady control volume form of Newton's second law. So, this F, the net force, is the sum of M1 and M2, as we already told you in the last slide. So, sigma x, where dmv dt is equal to M1 plus M2. Okay. Now, the question is, what are the forces acting on fluid in the control volume? So, one is gravity, other it's shear at solid surface, or pressure at solid surface, pressure on the flow surfaces. So, we can simply write sigma f as weight W due to gravity, pressure forces, solid surface pressure, and the force on due to pressure at wall and shear at wall. This is what we have just said. So, why there is no shear on the control surface? Because there is no velocity tangent to the control surface. There is no velocity that is tangent to the control surface like this. Okay. Now, going into a little zoomed figure, now we have indicated what M1 is, what pressures, what forces due to the the different pressure forces or the shear is there. This is the weight, as you can see, and this is the frictional or the shear forces Fx, Ssx and Fssy. These are the components of the shear forces in two different directions. Okay. So, forces by solid surface on fluid, and the momentum vectors have the same direction as the velocity vectors, as we have seen. Whatever the the direction of the velocities, the momentum will be in the same direction. So we can simply write F is equal to W plus Fp1 plus Fp2 plus Fss, and ma, force, mass into acceleration, is m1 plus m2. So we can simply write m1 plus m2 is equal to W plus Fp1 plus Fp2 plus Fss, and m1 here is minus rho q v1 and m2 is rho q v2 plus. An example we are going to see is the reducing elbow using this equation. We have seen this equation already in the last slide. Okay, this is sectional 1, this is section 2. The distance between this is 1 meter. Okay, so now the question is reducing elbow in vertical plane with water flow of 300 liters per second. Okay, so the Q is 300 liters per second. The volume of water in the elbow is 200 liter, that is the total volume. Energy loss is negligible. Calculate the forces of the elbow on the fluid. So this is the question. What is going to be the weight? Minus rho g into volume. So if you put volume as 200 liters, you are going to end with 1961 Newton in negative direction because weight acts downwards. Okay. Now we treat section 1 and section 2, right? We have to find the diameter is 50 centimeters. Okay, this is what we have seen, and diameter at section 2 is 30 centimeters. All right. So area will be 0.196 meters square in section 1 and area will be 0.071 meters square. The velocity is going to be 1.5. We know the discharge, right, and we know the area, therefore we will know the velocity. And similarly for section 2, this shows the direction. So this is the velocity direction at section 1 and this is the direction, velocity direction at the section 2 here in this way. Now the pressure is 150 kilopascal. Okay, we need to find the pressure at section 2. M is, because of all the values we know, we can calculate M as minus 459. How can you find M? That you can see in the slide below. Okay, minus rho q v1, m2 is rho q v2. You substitute that and you will be able to find m, and but the direction is same as velocity vector at section 1 and it will be 1270 Newton in this direction. Okay, so Fp is going to be 29,400 Newton. We are going to see actually a more detailed problem in the upcoming slides, but the pressure, the forces due to the pressure is 29,400 Newton here. Now we have to find out the pressure force here. Okay, so that is the problem. What is P2? How do we obtain P2? We can obtain P2 using the Bernoulli's equation. Okay, so P2 will be P1 plus gamma Z1, just rearrangement of this equation gives this equation, and we can simply substitute the values and obtain Z1 minus Z2. We already know it's minus 1 meter, V1 square minus V2 square by 2g. So V1 we have calculated, V2 we have calculated, everything is known. So actually P2 turns out to be 132 kilopascal. All right. Now if we know P2, we can calculate the pressure force. That will come out to be 9400 Newton. Okay. Now it's important to find out the horizontal forces. This is what we have done, is we have calculated the vertical forces. So the same m1 plus m2 is equal to w plus fp1 plus fp2 plus fss. So fss is going to be m1 plus m2 minus w minus fp1 minus fp2, or fssx in x direction, because there are two components. It will be m1x m2x minus wx minus fp1x minus fp2x. m1x, there is no component of 1 in horizontal direction because m1 was in this direction. W was again vertically acting, so this is a 0, and the pressure was also in this direction, vertical direction, therefore this is also 0. So Fssx is m2x minus f2x, and this is m2x is 1270 Newton that we already calculated, minus of minus 9400 Newton, this came to be 10.7 kilonewton. Very simple. Similarly, so this is force of the pipe on fluid. So this means that the fluid is pushing pipe to the left because Fssx is positive. Continuing with our example, we have to find out Fss in z direction or y direction. Basically we call this one as z. So m2z, because this is a horizontal, this is 0, and similarly with the pressure forces it is 0. So Fssz is m1 minus wz minus fp1z. So m1z we found out it was minus 459 Newton, weight we already found out, and this we just we calculated last time, I mean in the one slide before. So then this minus minus becomes positive, right, but still Fszz comes minus 27.9 kilonewton. So this means approximately 28 kilonewton force is acting downwards on the fluid because it is minus. Now pipe wants to move actually up, right, that is why the net force is in the downward direction. Now similarly there is something called moment of momentum equation. We are not going into detail, but just to show that here the B, capital B, for deriving moment of momentum equation we can assume m r into v, okay, moment of momentum, or m gamma into v. This r is actually nothing but gamma, and small b will be m r into v by m. So moment of momentum per unit mass. So actually the message here is that this equation is Reynolds transport theorem, can be used to derive any of these conservation principles, okay. So this is going to be 0, but we are not going to detail, therefore this is. So this is for steady state because this is del t for 0. We are not going to do the analysis. One of the examples is turbo machinery, but I am going to skip this for your convenience. But to know one of the examples of moment of momentum conservation equation in real life is turbo machinery. Now we can solve one practice problem. This will be based mostly on the Bernoulli's and momentum or mass conservation equation. So a jet of oil, relative density 0.80, issues from nozzle of 15 centimeter diameter with a velocity of 12 meters per second, okay. A smooth cone with vertex angle of 90 degree deflects the jet. The jet is horizontal and the vertex of the cone points towards the jet. Calculate the force required to hold the cone in position. So we have something like this. So this is the velocity of 12 meters per second. The diameter hole is 15 centimeter, and this is the cone, okay, and this is 90 degrees, okay. The jet is horizontal, okay, the vertex of the cone points towards the jet. So actually most important thing in these type of problems is first draw the figure, and then half our problem is solved. So we have successfully drawn the figure now. Now the solution steps is we consider the control volume as shown in the figure. So this is our control volume, you see. Okay, that is the first step. The pressure is everywhere atmospheric. As the cone is smooth, by neglecting the friction, the velocity of the sheet of water over the cone is v everywhere. The inclination of the velocity to the axis is 45 degrees, that we have simply assumed. Okay. So, the area is going to be pi by 4 d square, the area here, and rho is going to be its oil of relative density 0.8. So, rho is going to be 0.8 into 998 density of water, that is 798.4 kilogram per meter cube. So, the Q is area into velocity, AV. Area we have already calculated. So, area is here and this is the velocity that we already know from here. Okay. And this comes out to be 0.2121 meter cube per second. Okay. So, by momentum equation in x direction, so you see there is 0 if the reaction force here is Rx. Okay. So, 0 minus Rx, okay, is the change in momentum. And what is the change in momentum? It is rho q if the velocity v was there, v cos 45 minus v, or v can come out, you know, Rx is equal to rho qv 1 minus cos 45. You see here there is one force Rx that is going to act. So, and rate of change of momentum is rho qv 1 minus cos 45. You substitute the value rho qv 1 minus cos 45, and that is going to be Rx is equal to 595 Newton. By symmetry we can see Ry is equal to 0. So, hence the resultant reaction force on the fluid is R is equal to Rx. Thus, the force required to hold the cone in position is F is equal to 595 Newton along the negative x direction. This is one of the examples of this. In some point during the lecture series, we are going to solve more problems. We will have some sessions where we are going to solve only some random problems from fluid mechanics on the other topics that we are going to do. And I think this is enough, and this concludes our basics of fluid mechanics 2 section. We will start next week with laminar and turbulent flows. Thank you so much for watching.